All right, welcome to The Explainer. Today, we are diving into a word you've definitely heard, one that's famously confusing, but it's also fundamental to our entire digital world. And that word is entropy.
Yeah, you've probably heard it thrown around with words like disorder, uncertainty, maybe even surprise. And if you've always felt like those definitions are, well, a little fuzzy, you are not alone. So here's the plan. In the next few minutes, we're going to build up a really clear, intuitive grasp of what entropy actually is.
Okay, so let's get right into it. To really get what entropy is, we first have to understand the puzzle it was designed to solve in the first place.
And that puzzle, it comes to us from the mind of the absolute legend Claude Shannon, the guy they call the father of information theory. So picture this. It's 1948, and Shannon is just obsessed with this one super practical problem. How can we send a message using the absolute smallest amount of data possible, but, and this is key, without losing a single bit of the original meaning? We want the person on the other end to be able to rebuild it perfectly. It's this quest for total efficiency, with absolutely zero loss. So to really wrap our heads around this, we're going to do something cool. We're going to walk through the exact same thought process Shannon went through, but we'll use a really simple, everyday example to guide us. All right, so let's imagine we're sitting in Tokyo, and every day we've got to send a weather report over to a colleague in New York. Now, we're not going to waste time and data sending a whole sentence like, hey, the weather in Tokyo today is fine. Nope, we just need to get the core message across as efficiently as humanly possible. So let's try our first code. Super simple. Let's say there are only two options, fine or not fine. Easy, right? We can use just one single bit of information. A 0 means it's fine, a 1 means it's not. Perfect. It's totally lossless. You get the whole message. It seems like we've solved it, but what happens when we need just a little more detail?
Exactly. Because life is rarely that simple, is it? Not fine is way too vague. It could mean it's cloudy or rainy, or maybe it's even snowing. All of a sudden, our neat little one-bit system just isn't cutting it anymore. It can't capture the real world.
Okay, so we need to upgrade. We evolve our code. Fine, let's give that the shortest one, just 0. Cloudy can be 10. Rainy gets 110, and snow is 111. Now, the really clever thing here is how this is designed. It's unambiguous. See how no code starts with another complete code? That's on purpose. It means if you get a 110, there's no confusion. You know for a fact that means rainy. So yeah, it's still lossless. It's pretty smart. But here's the million-dollar question. Is it the most efficient code possible?
And this is where Shannon has his big aha moment. His truly brilliant insight. He realized that the key to ultimate efficiency isn't just about the messages themselves. It's about how often those messages actually happen.
I mean, just think about it. We're in Tokyo, right? A nice, fine day is super common. A snowy day, that's incredibly rare. So to be truly efficient, shouldn't our code reflect that reality? Doesn't it just make sense to give our shortest, cheapest codes to the things that happen all the time?
You bet. It would be just incredibly wasteful to use a long, clunky code for something that happens constantly. The smartest way to do it, the most intelligent design, is to look at the real-world probability and assign your shortest codes to your most common events. And making this one strategic change, it has a massive, massive impact on the average size of our messages.
And look, the numbers here really tell the story. A code that just ignores probability might average, say, 2.7 bits for every message we send. But when we optimize it for what actually happens in Tokyo, we can slash that average all the way down to just 1.42 bits. Now think about that over thousands and thousands of messages. That is a gigantic, game-changing improvement in efficiency.
Okay, this is awesome, but it brings up a really important question. How do we know when we've hit the jackpot? How do we know we found the absolute best code? Do we really have to just sit there trying out endless combinations, calculating the average every single time? I mean, that sounds exhausting.
Well, luckily for all of us, Shannon didn't just leave us with the problem. He also gave us the answer.
A beautiful, elegant, and super powerful mathematical formula that lets us find the absolute rock-bottom limit of compression. And he called this limit entropy, represented by the letter H, and he defined it as the smallest possible average size you can get for a lossless encoding. So think of this formula as the magic key. It's like a cheat code. It tells you, for any set of messages and their probabilities, what the theoretical best you can possibly do is. It's the target. It's the goal you're aiming for. Now, I know that formula can look a little scary, so let's just focus on the most important part of it, that little piece that says minus log base 2 of pi. All that part does is calculate the ideal number of bits a single message should take up based only on its probability. So let's take a coin flip. An event that happens half the time has a probability of 0.5. Well, minus log base 2 of 0.5 is exactly 1. So a perfect 50-50 event contains exactly 1 bit of what Shannon called information. And when we apply this back to our weather report, a really beautiful pattern just emerges. Fine, which happens half the time, probability 0.5, it has an ideal length of 1 bit. Cloudy, which happens a quarter of the time, probability 0.25, has an ideal length of 2 bits. And those really rare events, rainy and snow, at 0.125 probability, they each have an ideal length of 3 bits. Are you seeing this? It's so cool. The less likely something is to happen, the more information it carries, and the more bits you ideally need to describe it. So, when you take all those ideal bit lengths and you average them out, making sure to weight them by how often they actually happen, what you get is the entropy. And for our Tokyo weather scenario, that number is 1.75 bits. That's it. That's the floor. That's the fundamental limit. No compression algorithm, I don't care how clever or advanced it is, can ever do better than an average of 1.75 bits per message for this specific data, not without losing information.
Okay, so we've got the math part down, but now let's circle all the way back to the beginning. Remember those words? Disorder, uncertainty, surprise? How does this math connect back to those ideas?
Well, here's a really great way to think about it. A rare message, like getting the snow report in Tokyo, carries a ton of information precisely because it's so surprising. When you hear snow, it instantly eliminates all those other way more likely possibilities. But hearing the super common message, fine, that's not surprising at all, right? It doesn't really resolve much uncertainty for you, and so it contains way less information.
And this really gets us to the two extremes of entropy. On one end, you have a low entropy system. It's predictable. Imagine a loaded die that lands on 6 almost every single time. There's basically no surprise, so you get very little information from each roll. On the other end, you have a high entropy system, like a perfectly fair die. It's totally unpredictable. Every roll is a genuine surprise, so the average amount of information